In this module, we are going to take a look at OSPF adjacencies, OSPF authentication, and different network types that OSPF recognizes and uses on different interfaces. And to talk a little bit more in detail about what we're going to talk about, we are going to talk about the Hello protocol as used by OSPF. Here we are going to explore the parameters of the Hello protocol, what is contained in those Hello messages, how they are exchanged, and what is the information that needs to be there, and what is the information that is important. Then we are going to take a look at some detail and at some length at the different types of OSPF authentication, some configuration examples, and some misconfiguration examples in a case that you need to troubleshoot the OSPF authentication. After that, we are going to look in detail in something that is called the OSPF Adjacencies state machine. And this is the state machine, or the series of events, series of states that every interface and every neighbor goes through when the OSPF starts forming an adjacency on a particular interface, on a particular network. Then we are going to take a look at some of the optimizations that exist in OSPF when OSPF is configured on a multi-access interface, like for example on Ethernet interfaces. And for those of you who are thinking or reading ahead, this does mean that we are going to talk about the designated router, the DR, and the backup designated router, the BDR. And at the end, we are going to take a detailed look at different network types that OSPF recognizes. OSPF Hello protocol is a fundamental part of adjacency forming process in OSPF. This is the protocol, or I should not really maybe call it the protocol, but a sub-protocol, sub-function of OSPF that OSPF uses to discover, are there any neighbors on this network? Are there any OSPF routers on this network? Are these routers configured using a predefined set of parameters the same as me? And if they are configured in such a way, how to form the relationship, how to exchange the information and agree about this process. OSPF Hello protocol, or I should indeed say any OSPF messages that are being exchanged, are going to be sent using a special IP protocol number 89. So these messages are not UDP, they are not TCP messages, they are a separate IP protocol, 89 as I say. These Hello messages can be sent as either link local multicast with the destination of 224.0.0.5, or they can be sent as unicast, depending on the configuration and the network type that is in use. These messages are periodically sent, and the default timers are either 10 or 30 seconds, again depending on the network type. So here we have two sets of timers. Some are 10 seconds and some are 30 seconds, and very often when you are reading the literature about OSPF, the 10-second Hello timer is sometimes simply called the fast timer, and 30-second timer is sometimes called the slow timer. Now, which one is going to be used? Is it going to be the fast or the slow timer? Depends on the network type, and I'm going to talk about it when I talk about the network types later on. So these are the default values. Obviously, these values can be changed. These timers can be increased, and they can indeed be increased in such a way that this fast timer doesn't look so fast anymore. OSPF supports something that is called sub-second hellos, where we can send multiple hellos in 1 second. This is used in some high availability scenarios, but it may not actually be that good of an idea to do that, because it is going to consume some of the CPU resources on the router, and it is indeed going to consume some of the additional bandwidth just to maintain the relationship. Also, one of the timers that OSPF uses when it processes Hello messages is the dead interval. The dead interval has the value that is by default 4 times the Hello interval. So in a case that we are using fast timers, the default dead interval will be 40 seconds on those interfaces, and those interfaces that may be using slow timers with 30 seconds Hello interval, in that case we are going to have the dead interval by default of 120 seconds. And it's important to understand the relationship between these two. The default dead interval is not 40 seconds on Ethernet. It's 4 times the hello interval, which means that when we manually modify the hello interval, we are automatically, indirectly, going to modify the dead interval, because the default value is 4 times the hello interval, whatever the hello interval actually is. If we do not want to maintain this 4-to-1 relationship between the dead interval and the hello interval, we can manually modify the dead interval directly under the interface where we are configuring this. In the hello messages themselves, there are going to be certain important bits of information, certain important fields that are going to be used by OSPF to determine whether the neighbor we are hearing from is the neighbor that I like to call is viable to start building the relationship with. Those bits of information are router ID first. Now, router ID, you might recall from one of my previous elaborations on this subject, is simply an identifier, is simply a number, a 32-bit number that looks and feels like an IP address, but is not an IP address, that is used to uniquely identify our OSPF router in the OSPF network, which means that this router ID must be unique. If we had, for example, 2 routers that are directly connected to each other, and by some error, mistake, or misconfiguration, we ended up using the same router ID on both sides. Let's say that we had the loopback address configured with the same IP address, and this was used to generate the router ID. When these 2 neighbors start sending hellos to each other, they are not going to form any relationship. In fact, you are going to get an error message informing you that there is a duplicate router ID on the network. So this is not a legitimate situation in OSPF. Another important part of the hello message is going to be the area identifier and the area type, which is basically just an indicator, are we dealing with the stub or with the NSSA area. If the area IDs and type don't match on 2 sides of the connection, let's say that one router was configured one way and another router was configured in another way with different area IDs, for example, there will be no adjacency, because on the same interface the neighbors cannot become adjacent if these interfaces are configured to be in different areas. Also, we are going to have the information about the subnet and mask, and this is going to be verified in some cases, and in some cases this is not going to be relevant. For example, if we are dealing with the point-to-point interface, subnet and mask are not going to be verified are not going to be taken into account when we are forming the adjacency. On all other interface types, the subnet and mask actually need to match. We are also going to have the information about the hello interval and the dead interval, and 2 routers that are trying to form an adjacency. They need to agree about these values. And also, very, very important thing is that the routers in the hello messages are going to list the router IDs of seen viable neighbors. Now, what do I mean by seen viable neighbors? So let's say that we had 2 routers that are forming an adjacency, that are starting to form the neighborship. So let's say that we had our R1 and let's say that we had R2. When R1 sends the hello, it's going to include in its hello messages all these parameters that I mentioned, its own local router ID, the hello interval, the dead interval, the area ID, and so on. And it's also going to list the neighbors that it has seen. So let's say that this was the first hello that was sent on this network. And basically what is going to be listed here in the list of seen neighbors is going to be an empty field. Now let's say that at the same time, that this is all happening at the same time, R2 sends the hello message. So let's say that this was 1A and this is 1B. Router 2 is also going to say that, hey, you know what, I don't see any neighbors. But what has happened in the meantime is that by virtue of R2 receiving this message from R1, what R2 is going to do here is going to say, hey, look, it looks like I do see this router 1. And the same thing here is going to happen on R2. So for the second set of messages, when the hello is sent here, so let's say that this is hello message number 2A, what we are going to have here in the list is R1 is going to include R2's router ID, and it's going to inform R2 that, you know what, R2 actually has been seen by R1, and R1 agrees with those basic parameters in the message. And the same thing is going to happen in the hello message sent from from R2, we are going to have in the list of seen routers, we are going to have information that this router has actually seen the router ID of R1. At this point in the communication, we can say that our two routers have discovered about each other, that they have a so-called two-way communication. Now, two-way is a special state. It is part of the interface state machine that I'm going to talk a little bit later on. So, going back here, so there's going to be this list of seen neighbors in the list, and obviously we are going to have the information about the OSPF authentication that is in use. And I'm going to talk about authentication next, but what we are going to have here is the authentication method that is in use and whatever password, and I put password under the quotes because it's not necessarily always the password, it can also be MD5 hash that is being in use, but it's a two-stage process. There is going to be the method that is using the authentication type and whatever the authentication string is involved. So let's now go ahead and take a look at some of these parameters in iOS as they are actually happening. So what we're going to do next, we are going to go through a basic configuration setup of OSPF. So we are going to get very small OSPF network up and running. We are going to enable OSPF and then we are going to observe these hello messages as they are communicated on the network. As usual, I'm going to start very small. I'm just going to configure two routers that I mentioned before, R1 and R2, and I'm going to interconnect them using gigabit interfaces 1, and I'm going to run network 192.168.12.0/24 between them. So the first thing that I'm going to do is I'm going to configure basic OSPF on my R1 and I'm going to enable that OSPF on this gigabit 1 interface, which means that R1 is going to start sending hellos. Now, because this is an Ethernet interface, these are gigabit Ethernet 1 interfaces here, I'm going to do one extra step in configuration because on gigabit interfaces, or any Ethernet interfaces for that matter, by default OSPF is going to start the process of electing designated router and a backup designated router. But this is not something that I want to observe and talk about now. So what I'm going to do now is I'm going to artificially declare this interface here as point-to-point interface. And when the time comes to configure R2, I'm going to repeat the exact same process. I will make this interface point-to-point as well. But first things first, I'm going to now focus on configuring R1 in this way. I'm going to enable OSPF and I'm going to then observe the hello messages as they are coming. So how do I turn on OSPF? Well, the first thing that I have to do is I have to create a router OSPF process. And when I create a router OSPF process, I have to give it some sort of an identifier. This identifier here is a locally significant number, and I'm just going to run process number 1. And then under this process, I have to enable OSPF on a particular interface. So I'm going to say network 192.168.12.0, and with OSPF I have to specify the wildcard mask. So I'm just going to say 255 here, 000.255, and I have to tell OSPF in which area to operate on this interface. And I'm going to be very pragmatic and I'm going to run area 0. Now, what OSPF is going to do when it starts up, it is going to choose, it's going to select from one of the configured interfaces, and on my R1 I will have two interfaces configured. I will have gigabit 1 and I have gigabit 2 that is right now shut down, but it does have an IP address configured there. So my OSPF is going to pick one of these IP addresses, whichever is higher, and it's going to use that as a router ID. But in that case, I'm going to have a little bit trouble down the road when I start exploring the OSPF database and the information in certain show commands. I would every time have to tell you, you see this 192.168.12.1 here, this is not an IP address, but this is a router ID. So to avoid that, I'm also going to manually configure a router ID in my OSPF. So I'm just going to specify it here. And I'm deliberately going to use something that is not an IP address to show you that router ID is not an IP address. So I will on R1 use 0.0.0.1 as the router ID. Now, this is not a mandatory configuration in OSPF. I don't have to do this, but it's a relatively good idea to do, especially when you're learning how OSPF works, because that way you can have this clear distinction between, okay, this is a router ID and this is an IP address. And as we will see, in some show commands, you will be seeing both, and it's very, very important to understand which one of those is an IP address and which one is the router ID. So let's go ahead and configure this on R1. And as you might expect, every time before I configure any routing protocols in all of these demonstrations that we have went through, I always make sure that my underlying layer 2 is actually configured and operational. And this will be no exception. So on R1, the first thing that I'm going to do is I'm going to do show IP route connected. I want to see my 192.168.12.0 network connected to gigabit 1. And I want to be able to ping my R2. Even though to begin with I will be enabling OSPF only on R1 but not on R2, I still want to make sure that the connectivity between them exists before I proceed with this configuration. And I'm going to repeat the same thing on R2, and I can see that I do have 192.168.12 network in my routing table. So now I'm just going to ping from R2 to R1, and I do have the reachability. So let's now configure on R1, let's configure our router OSPF. So the first thing that I'm going to do here is I'm going to configure the router ID as I have described. But before I actually configure my network statement, which is going to enable OSPF on the interface as I described before, I'm going to do one more thing. And that one more thing is, you remember that I mentioned that I'm artificially going to configure my interface gigabit 1 to operate as point-to-point, and this can be done on the interface itself, and I'm going to use the command IP OSPF network, and I'm going to say point-to-point. So this is going to change certain behavior of this interface, but not by much. So let's do that. So I'm going to go here and I'm going to say IP OSPF network, and I'm going to say point-to-point. Now I'm going to go to my router OSPF1, and I'm going to use the network statement 192.168.12.0.255 area 0. Before I press enter here, I'm going to go to my Wireshark and I'm going to start collecting traffic from my Ethernet interface 1, and I want to collect only OSPF traffic. I will be collecting all the traffic, but I want to display only OSPF traffic because at this point I really don't care about anything else. So what I can see now is that my R1 has started periodically sending hello messages, and we can see here that we have already received 2, and here based on the time we can see that they are roughly 10 seconds apart, and this is the default hello timer on broadcast and point-to-point network interfaces. So the first thing that I want to do now is I want to open this OSPF part here, and I'm going to expand this capture information here to show you a couple of things. The first thing that we can see here is that my hello packet is divided into several sections. The two that we care about is the OSPF header and the contents of the hello packet itself. And here in the header we can see what version of OSPF we are running, and if you are running OSPF configured as I'm describing, you will always see OSPF version 2. For IPv6 you will be seeing OSPF version 3, but this is not what we are looking at right now. Also, we are going to see what kind of message type we are dealing with, and we can see that this is actually hello packet. We can see what is the source of this hello message, and here it's significant to see that this source is not going to be an IP address of the OSPF packet. It will be actually the router ID that sends this information, and we can see what is the area ID, and we can see that the area ID here is specified as 0, which represents the backbone area, or area 0000. Also, we can see that there is no authentication configured. We can see that the authentication type is null and that the authentication data is none. I will talk about authentication in just a minute. And then finally here we can see in the OSPF hello packet section, we can see what is the actual network mask that is configured, and the IP address can be determined based on the source IP address of this hello packet. So we know what the source IP address is and we know what the mask is in use, so the other side can determine whether the host that is sending these hellos is on the same subnet as it is locally. And we can also see here claimed hello interval. We can also see what is the dead interval, and remember that by default dead interval will be treated as 4 times the hello interval, but when we send the hello packet, we are not relying on this multiplication for it. In the hello packet, we actually need to specify, or the router that sends this, the router needs to specify what is the dead interval. And also in a case of broadcast and non-broadcast network types, the hello packet will contain information about what is the designated router and what is the backup designated router. But because I'm using point-to-point network type where this selection doesn't happen, these values will always be 0. So now I can see what are the contents of hello packets. But one more thing that I want to show you before I proceed is this option field. Now in this option field, which is basically just a bit field here, we can see that certain values are set to 0, certain bits are set to 1. This is where we are going to have information whether this is a stub area or the NSSA area. If this bit was set to 1, this would be NSSA area. Now we can see that this bit is set to 0, so we can see that the not so stubby area is not supported. And we can see that the external routing capability is supported, so this bit is set to 1, which means that this area is not a stub area. If this bit was set to 0, this would represent that the stub area is in use. So it's important when we talk about the area ID, this is specified here, but the area type is actually specified in this options bit field. At this point I could go back on R2 and enable OSPF and the adjacency is going to come up, but I don't want to do that just yet, because I want to now explore how the OSPF authentication actually works. So now we are going to talk about the OSPF authentication. Now, the reason why I don't want to enable that adjacency just yet is that then my routers are going to go through the adjacency state machine, but I would first like to talk about it a little bit before we explore it. But we can look at the authentication even without any OSPF being configured on R2. So what is the OSPF authentication? First thing that we need to understand about OSPF authentication is that it is always present in the hello packets. We have observed in our hello packets here that even though we haven't configured anything, we do have information about what kind of authentication is used. And we can see here that it says null. Null authentication is still an authentication type when it comes to OSPF. It doesn't actually carry any password or any key with it. It's always going to be an empty field, but if that field doesn't match what is configured on the other side, we are still going to have the authentication type mismatch. So if we had two neighbors like we have R1 and R2, and they are sending hellos, and this one here claims that the type is null, and this one here claims that the authentication type is, let's say, plain text, we are still going to have an authentication mismatch even though we haven't actually configured any password on R2, because OSPF authentication is a two-step process. The authentication type needs to match, and if the authentication type matches, then the authentication string, authentication password, or the key, that needs to match as well. And OSPF supports 3 types of authentication. It supports authentication type null, and you might guess that this is going to be represented in the hello packet with the value of 0, and this is the default authentication. Or we can have plain text, which will be represented with the type 1, or we can have MD5, which will be represented with type 2. Now, you might be thinking, why is this important? Why do I need to know whether this is type 0, type 1, or type 2? Well, there is a simple reason for that. If you are having an authentication problem in OSPF, and if you are troubleshooting the adjacency between the two routers, if the authentication type doesn't match, and when you are running a particular debug, and I'll show you which debug command you can run to see this, what the iOS will tell you is that there is a locally configured type and then the number 1, 2, or 3, or sorry, 0, 1, or 2, and the remote side is configured to use 0, 1, or 2. So you need to understand what those three values mean. Luckily, it's very easy to remember. 0 is null, plain text is 1, and MD5 is 2. Being a two-stage process, OSPF authentication also reflects on the way it's configured. So we have to configure both of these stages of authentication. We have to configure the method, and we have to configure whatever password or key we are using. When we are configuring the method, there are, generally speaking, two ways to configure it. One is on per area basis, and another one is on per interface basis. When we configure area authentication, we can still override those settings by going on a particular interface, and even if that interface was in the area where we say enabled MD5 authentication, we could still override behavior on that one particular interface and change the authentication type to something else. In both cases, regardless of how we configure the authentication method type, when we are configuring the password or the key, this needs to be done on per interface basis. And here it's very important to remember that the authentication password or the authentication key is configured using different commands for plain text and MD5. I'm going to show you this, but before I do, let's take a look at how would we, for example, configure and force no authentication if that authentication wasn't configured already. So here is an example of how null authentication is configured. So here I have two examples. One is how would we configure authentication of null type for area 0 to be the default. Now keep in mind that typing this command is only required if you have already had some other authentication type configured for area 0. This is the way to return to normal. And if we enter this command, we are not really going to see it in the running configuration because this is really the default behavior. The second example is if we said, for example, on area 0, we had some other authentication method configured, and on interface gigabit 1, we wanted to force the null authentication. We can do that if we go under the interface and enter the command IPOSPF authentication null. This is going to change the authentication from whatever it was already configured on per area basis or on that interface, and it's going to change it to the null type authentication. And here is the example of how to configure plain text authentication. Again, I'm going to show you several examples. The first example here is configuring the plain text authentication on an area basis. So using area 0 authentication is going to enable plain text authentication in area 0. You might remember that even though we have enabled the area authentication, we still need to configure the password to use. And here is the example of configuring the password on gigabit interface 1. And we can configure the password using IPOSPF authentication key and then specifying the password. There are three ways to specify this password. One is to simply just type password, and the other one is to type 0 followed by unencrypted password, which is actually what is going to end up in the running configuration if you just type the password. And the third way is to use type 7 authentication, type 7 encryption, and then encrypted key will follow. And if you use command like, for example, service password encryption to encrypt all the passwords in your router, this is what you are going to end up seeing in the running configuration. But remember, type 7 keys, type 7 passwords are reversible, so this can be easily decoded. It's not completely safe, or it's not a one-way hash. We can always reconstruct what the password was. And here in this last example on interface gigabit Ethernet 2, let's say that we had a different authentication method configured on per area basis. This is an example of how we can enable plain text authentication on that particular interface. Again, remember, 2 steps. One is configuring the authentication type, and we do that with IP/OSPF authentication. The second step is configuring the authentication key, and we are going to use the same command that we used here, but I have used a different example here. I have used it with 0 followed by the password. And remember what I said, even though you have entered the password like this, what is actually going to end up in the running configuration as the result will be this format here. And one more example here, how do we configure MD5 authentication? Again, I'm going to show you how to do it with the area authentication and on per interface basis. If we wanted to enable MD5 authentication on per area basis, we would go into the OSPF process, area 0 authentication, message digest. This message digest tells the router to use MD5 authentication. And we specify the key by going under the interface, IP/OSPF message digest key, key ID, MD5, and then the string. Again, there are 3 ways to configure this, again, by just typing the password, by typing 0 followed by password, or 7 followed by type 7 encrypted password. If we wanted to configure message digest authentication on an interface to override per area settings, this is how we would do it. Again, 2-step process. The first one is IP/OSPF authentication message digest, and you can see here that it's a very similar command set as we would do it on the area. We are simply saying on this interface, use this authentication type. And then we would specify the key just like we did here, but again, I have used an example with 0 followed by password. A very, very important thing to note here is a common misconfiguration when configuring OSPF authentication. And here is an example of this very, very common mistake that people do. So here I just listed the interface configuration. What do you think is configured here? Well, obviously, we have configured here the authentication type to be message digest. But what is going to be the password used for this authentication on this link? It's going to be nothing. It is going to be an empty string. Why? Because this line here, IP/OSPF authentication key Cisco, configures the password to be used with type 1 authentication. And this here configures type 2, MD5 authentication. This one here configures the password to be used with the plain text authentication. So, and imagine the same thing in just a reverse order. You can easily configure, for example, IP/OSPF authentication and IP/OSPF message digest key 1 MD5 Cisco. In that case, you're configuring plain text authentication type with no password because you have not specified the key. Be on a lookout for this misconfiguration, especially when you are troubleshooting something, because this is a very, very common thing. This is a very common authentication problem. Now, how do you verify and troubleshoot your authentication settings in OSPF? Well, first thing that you need to make sure is that your type and password are compatible. In other words, make sure to avoid this situation here. The second thing is, if you are using MD5 authentication, your key ID must match. That means that if you have 2 routers that are configured for MD5 authentication, and this one here is sending key ID with 1, and this one here is sending the key ID 2, there will be no successful authentication. For MD5, the key ID actually needs to match. And also you can see what are your active settings on a particular interface for the authentication with show IP/OSPF interface command. And if you scroll all the way down at the end of that output, you are going to see the authentication settings. So if I go here on R1 and if I say show IP/OSPF interface gigabit 1 all the way down, I'm going to have the information about what authentication is in use. And as you can see here, I'm not seeing anything, which means that the null type is in use. Let's change it. Let's go into our router OSPF 1 and let's say area 0 authentication. Now what I'm doing, now I have type 1 authentication configured, and if I do show IP OSPF interface gigabit 1, I will see here now that it says that a simple password authentication is enabled. But it doesn't tell me what is the password in use. It doesn't tell me what is the password in use because I have no password in use. And let's verify that. So I'm going to go to my Wireshark now and I'm going to restart the capture here. And I'm going to get the authentication information here. So when the hello arrives, I will see now in the authentication part of my hello that now it says that a simple password authentication is in use. But take a look at the authentication data. It's an empty field. There is nothing used as the password. So let's go back here and let's configure the password. So I'm going to say IP OSPF authentication key. Oh, actually I have to do it on the interface. Interface gigabit 1, IP OSPF authentication key, and here you see that I have two options. I can use either 0 or 7. So let's do password Cisco. So now if I go back to my Wireshark and let's wait for the hello to arrive. Now when I take a look at this, I will see now that the authentication type says simple password, and I will also see that now I do have a plain text password transmitted there. And if I repeat my show IP OSPF interface gigabit 1 command, I will see now that it says there simple password authentication enabled. Again, for the simple password authentication, you are not going to see the password. You actually have to take a look at the interface or you have to capture the traffic. Let's change this to MD5. So I'm going to do that on the interface. So just a quick reminder what I have configured now. What I have now is interface gigabit 1 is configured to specify the key for plain text authentication, and I have area authentication enabled, which means that I have plain text enabled on all interfaces in area 0. But now on interface gigabit 1, what I'm going to do is I'm going to say IP OSPF authentication, and I'm going to specify the message digest now. If I go to my Wireshark at this moment, now this is interesting thing. I have not seen this message before, and this is probably relatively new. I'm using this iOS that I have not used much before, and in some of the older versions of iOS you don't actually get this message, but it's a good thing that Cisco does it now. It tells me no valid authentication key to send, and this is true. And if I go to my Wireshark here and if I take a look at one of the last packets here, I will see here that it says authentication type, it says it's cryptographic, it says authentication key ID is 0 because there is really no key, and here is the authentication data, but this is an empty string. But you are always going to have some information there sent because we don't really want to advertise the fact that we are not using any key. If I do show IP OSPF interface gigabit 1, now what I will see here, and this is very important, here at the end I'm going to see the information that the cryptographic authentication is used, and depending on your iOS it may actually say MD5 authentication, but in a case of MD5 authentication configured, you are going to have the information what key you are using. And when we have a misconfiguration like we have now, which is the exact same one as I've shown you in the slide, you are going to get the information that there is no key configured. So let's fix that. Let's say, for example, IP OSPF message digest key, and here I have to specify key ID. Let's use key ID 1, MD5, Cisco. So now I have configured the key. If I do show IP OSPF interfaces gigabit 1, now I can see that not only my cryptographic authentication has been enabled, I can also see which key ID we are using, and we can see that we are using key number 1. If I go back to Wireshark and I take a look at the hello packets that are being captured, I can see here that we are using authentication key ID 1, and we can see here that there is some authentication data, but because this is not plain text, we cannot actually figure out what the password is. And while we are on the subject of authentication, and for this I'm just going to go away a little bit, virtual links are a special kind of virtual interfaces used by OSPF to interconnect discontiguous area 0, discontiguous backbone area. And I'm going to talk about virtual links a little bit more later on, but for now I just want to show you here the examples of configuring authentication for virtual links. So if you wanted to have no authentication on the virtual link, you would specify that with using authentication null after the specification of the virtual link. Now, important thing to remember about virtual links is that they are always perceived to be in area 0, no matter what area is configured to be the transit area for them. Virtual links are always considered to be interfaces in area 0. That means that you are going to be specifying these authentication settings here only if you want to override area 0 pre-configured authentication. Let's say that in this example number 1, we might have area 0 configured with the message digest authentication, and for whatever reason on the virtual links we didn't want to use that. This is how we would override it. Also, if we wanted to change the authentication to be plain text, we would say authentication, and which enables plain text authentication, and then we would have to specify the actual key to use here with using authentication key Cisco. But if area 0 authentication was already configured, if you already used plain text authentication, you can skip this part here and just type area 2 virtual link, whatever the router ID of the destination is, authentication dash key, and then the password. The same thing for message digest. If we wanted to override the settings, we would say area, whatever transit area it is, virtual link, the destination, and then we would say authentication message digest. So this would override the area settings if they were set to be something other than MD5. And finally, we would set the MD5 key here. Again, remember that you need to specify the key ID followed by MD5 followed by the actual password to use. And if message digest authentication for area 0 was already enabled, you could skip this part here and just type area, whatever the transit area is, virtual link, destination, message digest key, key ID MD5, followed by whatever the password is that you want to use. The next thing that I'm going to talk about is going to be OSPF Adjacency State Machine. Now, OSPF Adjacency State Machine is the set of states that every neighbor, every interface goes through when they start forming the relationship. It consists of several steps, and understanding what happens in each of these steps is going to be very, very important should you ever encounter a situation in which you have to figure out why the adjacency isn't coming up. And the adjacency state machine goes, generally speaking, through init state, two-way state, exchange start, exchange, loading, and full state. Depending on the interface type, depending on the network type, you may or may not first go through the wait state. Wait state exists only on those interfaces that have DR and BDR election, which means broadcast or non-broadcast network types. And in this state here, basically an unnecessary DR and BDR election is being avoided. Now, two of these states I have underlined. These are the two-way and the full state. These are possible stable states. Now, what it means by possible stable state is that you may have a situation in which your neighbors are in either one of these two states and everything in your network is still operational. Now, with the full state, this is no big deal. This is what you would expect the neighbors to be in and have fully operational network. But the two-way state here may be a little bit unusual, but there are situations in which your neighbors do have a two-way relationship and everything is still okay in the network. I will go in each and every one of these states in greater detail, but before I do that, I would like to show you, or I would like to introduce you to a couple of commands that you can run to verify and troubleshoot the state machine. The first one is how to verify the local state, where your interface is. And for that you can use show IP OSPF interface, and you can use the brief version of this command. And this will show you on a particular interface in which state of these states here your interface is. Also, the neighbor state, you can see in which state is the neighbor you are just about to form the relationship with show IP OSPF neighbor command. If you want to observe the adjacency process as it is going through these states and as it is forming, you can run debug IP OSPF adjacencies command. Now, I always pronounce this as adjacencies because I really don't know how to pronounce ADJ. Should I pronounce it as Adj or ADJ or Alpha Delta Juliet? I don't really know. But what we want to do here is we need to understand how to observe these states. But when we are observing them, it doesn't tell us anything unless we know what is happening in each of these states. So let's go through the list of these states and see what do they do. Now, the first state, as I mentioned, that you might encounter is going to be wait state. Wait state is existing only on broadcast and non-broadcast network, and the purpose of it is to avoid unnecessary designated router and the backup designated router election. I'm going to talk about these elections in just about a minute. And the routers are going to spend a fixed period of time in this state. And the fixed period of time that the routers are going to spend in this state is going to be the dead interval time. So if you have a dead interval that is unusually long, don't expect your adjacency to form because the routers need to spend this much time in that state. Now, you may remember that when we configured our example with R1 and R2, I did declare that interface as point-to-point. And I said that I'm doing that to avoid unnecessary DR and BDR election. I lied to you a little bit. What I was doing there, I really didn't want to wait for 40 seconds before I start observing things on that interface. So I was doing that to avoid the wait state. Once the neighbors are out of the wait state, they're going to enter the init state. In the init state, basically what is happening is the hellos have been sent. Now, you might recall that when we send the hellos, we are including our own set of parameters in these hellos. And one of the set of parameters is the list of seen neighbors. The routers are going to be in the init state before they actually observe their own router ID in the incoming hello. So this wait state means that we have sent the hellos. We might actually be even receiving the hellos from the neighbor, but what we are not seeing is our own router ID in these incoming hello messages back. The moment we see our own router ID in the incoming hello message, at that moment we know that we have a two-way state with our neighbor. The two-way state simply means that the neighbor can see us and we can see the neighbor as well. But before I go to the two-way state, what would be the cause of the neighborship relationship to be in the init state for unusually long time? Well, that depends. If we are sending the hellos and the neighbor on the other side is not seeing the hellos, what we are going to be observing on our local interface. So let's say that we had two routers, again, our R1 and R2. And let's say that R1 is sending the hellos to R2, and for some reason these hellos are not making it to the R2. If we do show IP OSPF interface for this interface here, we are going to see that this interface here is in the init state. But if we go to R2 and if we do show IP OSPF neighbors, we are not going to see R1 because we are not seeing the hellos from the neighbor. But imagine this situation. Imagine that these hellos are actually making it all the way to R2, and R2 is responding but for some reason we are not receiving the hellos back from R2. In that case, when we go to R1 and if we do show IP OSPF interface here, we are going to observe that this interface is in init state. But if we go to R2 and we do show IP OSPF neighbor, what we are going to see is we are going to see R1 in the init state. But if we see R1 in the neighbor table, that means that we are receiving the hellos from R1, but for some reason R1 is not actually receiving our hellos. So when you are troubleshooting this situation that the neighbors are actually stuck in this init phase, it's important to understand, is this communication going this way or is this communication going this way? So now that we know that, let's take a look at what other states we have there. So, two-way state. As I said earlier, two-way state is a possible stable state. And when we are going to have a possible stable state with the two-way is in a case when we have a network where we do have an election of the DR and the BDR. And I'm going to talk about it in great detail in a moment, but let's for a moment think that this router here is the DR and that there is no BDR in the network. What's going to happen here is that these two routers, let's call them R1 and R2, they're going to form a full adjacency with DR. But because they are sharing the same segment, they are also going to be seeing each other's hellos. And if they see each other's hellos, they will be including each other router IDs here, which means that they are going to have a stable two-way relationship in this case, but they are not going to proceed anywhere from there because the adjacencies are only going to be formed with the DR and with the BDR if the backup designated router existed in our network. And as I said, I'm going to talk about this particular thing in greater detail later on, but I'm just now giving you an example when and under which circumstances you can actually observe that there is a stable two-way relationship that doesn't seem to be progressing anywhere else. So the routers are going to enter this two-way state when they have received an incoming hello with its own router ID in the list of seen neighbors. But now let's say that these routers actually do want to proceed and form a full adjacency. The next stage, the next step in adjacency state machine that they are going to enter is something that is called the exchange start. Sometimes this is simply called the X start phase. In the exchange start, there are a couple of things that happen. The first, a master-slave relationship is going to be established between the routers that are forming the adjacency. Now, this master-slave relationship simply means which one of these two routers is going to decide when we can move on to the next stage. And the selection of the master-slave is very, very simple. The router with the higher router ID is going to become the master and the one with the lower router ID is going to become the slave. There is no way to influence this behavior and there is no need to influence this behavior because it's really not that significant. Now, what is significant here is that in this stage of adjacency forming, the routers need to agree how are they going to exchange the information down the road. In other words, how much information they can send to each other and make sure that they are receiving this information. To do that, the routers are going to exchange the information about what is the locally configured maximum transmission unit, the MTU, configured on the interfaces on which the adjacency is being formed. So if we have two routers, our R1 and R2, and let's say that this router here was configured with 1500 bytes of MTU, and let's say that this one here was configured with 9000 jumbo MTU, what's going to happen? They are not going to agree on this value, and this adjacency is going to be appearing to be stuck in the exchange start phase. So there are two ways around this problem. One, and the more preferred way, is to actually go to one of these interfaces and modify MTU to match the other side. If that is not possible or this option is simply not available to you for whatever reason, there is a way to tell the routers to actually ignore this bit, and you can do that under the interface configuration here with the command of IP OSPF mtu-ignore. So the command is IP OSPF mtu ignore. But if you are doing this command, you are telling the routers, you know what, just don't stop here if the MTUs don't match, proceed on, but you are opening yourself for a possibility that they won't be able to exchange the information, especially if the side with the higher MTU has a relatively large database and it attempts to send that much information in a single packet, which the other side may not be able to process if it receives it. So this is why I said that the more preferred way of actually resolving this issue would be to correct the MTU settings on the interfaces. After the routers have agreed on this, they're going to proceed into the exchange state. In the exchange state, OSPF packets called the database descriptors, or the DBDs, are exchanged. The contents of DBDs are simply the list of available link state advertisements, the LSAs, that exist in routers' databases. But keep in mind that these are not actually the LSAs being exchanged. This is information about which LSAs are available. So let's say that we had two routers, again R1 and R2, and let's say that R1 here in its database had a large number of LSAs. Now each one of these LSAs, when expanded, is going to have a certain parameters, it's going to have a certain data, and the LSAs themselves are a lot of information to carry. But the information about which LSAs we have is a relatively short piece of information. Now imagine that this database here that existed on R1 also existed on R2, and the only difference was this one LSA. Is there really a need for R1 to send entire database here only to have R2 discard large part of it because it already has it? Well, you might guess it. There is no reason to do that. But how is R2 going to know what information is available on R1? Well, this is exactly why we have the exchange phase. Because what's going to happen in the exchange phase, this information about the database, which LSAs are available, so we can say that this is simply the LSA summary information, or the table of contents, or the menu, call it whatever, is going to be communicated from one router to the other. So this is going to be a relatively small piece of information where each LSA is identified with its link state advertisement identifier, the originating router, so it's going to be the originator, and this is going to be the router ID of the router that actually injected this LSA into the OSPF domain, which is information that is preserved here. There is going to be a sequence number about this LSA and the checksum. So this information is going to be communicated between the routers. So when this router receives this information about what R1 has in its database, it can actually say, okay, I don't need this, this, or this, but you know what, I don't seem to have this LSA. So now R2 knows that this information is missing from its database, and it can actually request from R1 to send this information. And the exact same thing is going to happen in the opposite direction. R2 is going to send its own summary information to R1. So this is the information that is going to be exchanged in the exchange state. Now, when the routers have determined the list of these missing LSAs, as I call them here, so the LSAs that they might need from each other, they're going to enter the loading state. Now, the loading state simply means that the list of missing LSAs is going to be processed. For each LSA that we are missing, the router is going to send a link state request. The router that has this information is going to respond with the link state update, and when this information is received on the other side, we are going to acknowledge it with the link state acknowledgement. So let's again take a look at this example here. Let's say that we had the list of LSAs on our R1, and R2 has determined that it doesn't need these LSAs here, but it does need this LSA, and let's say that this is LSA, let's say LSA B, whatever, or yeah, let's call it B for whatever reason. So what R2 is going to do here is going to send the link state request for B. It's going to ask from R1 to send it B. Now, R1 is going to respond with a link state update message, and it's going to say, okay, here you have B. And then R2 is going to confirm that it actually received this information back, so that R1 knows that whatever it sent to R2 has been received by R2. When this entire list has been processed, when we have went through the whole list on both sides, the neighbor is going to enter a full state. And this is a stable state. This is where you do want to have the neighbors. At this point in time, the routers can run the Dijkstra algorithm, they can run the SPF algorithm and calculate their internal routing tables. Now, this process of going through the adjacency forming happens only when the neighbors first discover each other. Once they enter the full state, what is going to be happening there? If there is a significant change, or not significant, if there is a change in the database, a new LSA needs to be injected, we are simply going to inform our neighbor that, hey, look, I do have this LSA, do you want it? The neighbor is going to say, yes, I need it, link state request, link state update, link state acknowledgement. Periodically, and in iOS, this is going to happen every 30 minutes, the entire databases are going to be reflooded through the network. This process can be disabled, but in iOS, this refresh of the routing database information, of the OSPF database information, happens by default every 30 minutes. Now that we know how this works, let's go back to our R1 and R2, and let's finish up our configuration. So what I'm going to do now is I'm going to go to R1, and I'm just going to verify what configuration